So welcome back. So now we are towards the end of this part of primary and secondary features. Few more slides and then we'll move to the topic on plate tectonics. This is also very commonly observed feature in tectonic deformation on a regional scale as well as on local scale, and that what we term as a slicken sides. Okay, and slicken sides to some extent are helpful in identifying the sense of movement. So I hope you people are aware of what is strike and what is dip and rake. So usually the rake is the direction which will help us in identifying that in which direction the displacement has occurred. Okay. So the slicken slide are the polished and stratified surfaces formed due to movement of rock masses or the unconsolidated sediment columns along a fault plane, and a very important feature in determining the direction of recent movements. And basically if you take the definition of the rake, then the rake is the angle between the strike of a plane and a linear feature within that plane, and this gives the direction of the displacement. So direction, that is the in which direction it has moved. For example, you have these striations over here, and this will be the strike, and the amount of depth will be what we call as the exactly perpendicular. So this will be the amount of depth here, and this will be the movement of the indicating the based on the striations. So this will be your rake, and mostly this type of features are been seen when we are able to look at the strike slip faults. So this part will become more clear when we are talking about the strike slip fault, but as a part of the contacts or the features, you can just remember this. Okay. So this is the direction, and this is the rake, or in the direction in which the faulting has occurred, okay, or displacement has occurred. Few important terms before moving into the some details of the paleoseismology is the active faults. Of course, we have a major topic which we are going to talk about, the active faults, but the general definition, if we take, these are the faults which are likely to have another earthquake in future, and faults are commonly considered to be inactive if they have moved one or more times in the last 10,000 years. Okay. Aseismic is the term which has been used to describe a fault on which no earthquakes have occurred or been observed. Coseismic is the term used to describe the instantaneous deformation during earthquake in landforms or along the fault. So these are few terms which we should keep in mind, because we will be talking mostly about the active faults, coseismic ruptures, and aseismic deformation. So this part will end, and we'll start with the new topic, and that is on the plate tectonics. Okay. Now coming to this part, I'll be slightly quick, because this basically we are talking why we have considered this and why we are talking about the plate tectonics, because we need to understand the deformation on global scale. And as we have discussed in a couple of previous lectures, that we need to understand the deformation or the tectonics on the global scale, then regional scale, and then coming down to the local scale. Okay. So global scale is important, because that will tell us that the deformation pattern we can expect in a tectonically active or seismically active regions. Okay. So, for example, I will just tell you few points in the beginning that we have or we very well know about that there is a collision zone between the Indian plate and the Eurasian plate, and the result what we see is the mighty Himalayas, and those are all folded mountain chain. So, we are coming down from the global scale to regional scale, and then further site specific if we come, or the local scale, then we are talking about the folds and faults. Okay. So, crustal deformation and mountain building activity, if you take, is on the global scale and its implication towards earthquake hazard. So, of course, the picture which you see here is from the higher Himalayas, taken from Kangra Valley, a beautiful landscape, but along with the beauty we also experience, or we know that we should know that there is a hazard associated with this, and that hazard is mainly the most common is the earthquake. So, before getting into the plate tectonic parts, some of you might be aware of this, but I will quickly move so that the new students who have taken this course should also understand the overall process. Okay. Earth to some extent is very important for us to understand, because the plate movements what we see, and plate movements from its original location millions and million years back, and what is the present configuration in terms of with respect to one another, with respect to their plate boundaries between that exist between these plates is extremely important. So, the interior of Earth, mainly the asthenosphere, is the important unit which is responsible for the movement of all the plates. Okay. So, plate tectonics mainly talks about the plate movement. Okay. So, it is the movement of plates and the forces acting on them. Okay. It explains the distribution of volcanoes, earthquakes, folded mountain chains, rock assemblages, and sea floor structures. So, this we are talking about on the global scale. The forces that drive plate motions arises from the mantle convection system. So, for this purpose, okay, we need to at least know that which layer or the portion of the interior of Earth is responsible for driving the plate, the different tectonic plates or lithospheric plates we can talk about. So, this usually we look into try to connect and try to understand that what is the connectivity between the different cycles. Okay. So, on the larger scale or the global scale, as we were talking about the plate tectonics. So, the tectonic cycle usually this keeps going on. Okay. So, you have the building up of the oceanic crust, and that oceanic, and then the plates are moving away from one another, getting subducted, and then we have the volcanic eruptions, and this plate will be consumed further. So, what we see when it goes down, then we have rock melting, or the crust is getting melted, and the new crust has been formed, or the new material is coming out in form of lava, and then which forms the igneous rocks and all that. And due to deformation, we have the mountain building activity, and that will be subjected to erosion, weathering and all that, and the sediments are being formed, and then those sediments getting consolidated, resulting into the formation of sedimentary rocks, deformation under high temperature and pressure, and then result into the foliated rocks and non-foliated rocks, or what we can metamorphic rocks. Again they are melted in this process, and then this cycle goes on. So, there is a connectivity of this, as well as the connections or the connectivity of the cycle, what we call as an erosion. Okay. So, all these cycles, hydrological cycle, rock cycle and tectonic cycle are been connected, and the 3 cycles are basically been governed by the geothermal energy, which is coming from the interior of earth, and the solar energy which we receive from the sun. Okay. So, just keep in mind, go through it in detail, so you will be able to understand that where we are looking at the connectivity. So, the deposition, erosion, because of the environment where the rocks are exposed, and the deformation will result into the folding of the material, and then the erosion, formation of rocks and all that, and the plate tectonics will keep on adding new crust, melting the old one or getting the old one beneath into the asthenosphere, then coming out in the form of. So, this cycle keeps going on. So, if you look at the interior of earth, I am not going to get into the details of this, but for us this unit, that is to know that this unit is important, because this asthenosphere is responsible for the movement of the tectonic plates, that is oceanic plate and the lithospheric plate. Now, the isostasy, basically we look at that the oceanic plate and the continental plate has been shown here. Okay. They are basically floating on the partially molten layer, that is your asthenosphere, and depending on the density of this plates, because the oceanic plate, if you take this is the oceanic plate here, they are heavier, whereas the continental plates are comparatively lighter, okay, in terms of the density. So, they will float on the partially molten layers at different elevation, and it has been understood to some extent, because this process takes like in geological time scale, it will take long time, but in overall it has been understood that this balance, okay, or the plates will try to keep themselves in a balanced form. Okay. So, the principle of isostasy governs the rise or subsidence of the crust until the mass is buoyantly balanced, because they are floating on the partially molten units. Because of isostasy, all parts of the lithospheres are in a floating equilibrium. So, if you erode the upper portion which is exposed of any plate, then it will again rise up and try to balance itself. Okay. So, the low density wood, for example, okay, float high and will have a deep roots. Okay. So, here the low density, if you consider in terms of the earth crust, then what we are having, the low density is your continental plates. Okay. So, the continental plates usually will float high and will have deep roots, okay, whereas the high density blocks. So, in this case, the high density block is having your oceanic plates, which floats low and will have shallow roots. Okay. So, this is an example which has been given here. Is a low density block floats higher. So, you have and will have deeper roots, whereas the heavy blocks will have will float low and will have shallower roots. Okay. So, they will not have the deeper roots, but the lighter one will have deeper roots, and they will also float higher. And this is overall, if we see, is important in terms of the erosion, and then what erosion will trigger, because if there is a continuous erosion of this, then it will keep coming up actually. So, if we look at these two examples which have been given on the right hand side, we have with respect to the earth mantle and the continental lithosphere, and on the left hand side what we see is the ocean water and the iceberg. So basically, as soon as the density of the material varies, it will show a different elevation or a different the deeper roots and all that. Okay. So for example, if you are having the frozen when water freezes, it basically changes the density and which becomes lower as compared to the water. Okay. So it will float on the surface of the water and will have almost like whatever you see on the surface, that is an iceberg, which is hardly 10%, but will have the deeper root below the water surface. Okay. So you're having 90% of the volume is submerged, and similar is in case of the continental crust. Okay. So you have like similar to the iceberg, many large mountain ranges, approximately 80%, 84% of the mountain range of the continent rocks are around 2.7, that is the density, and will submerge in the mantle. The mantle density is higher, okay, and will have the deeper roots. Okay. So if what we see as in mountains on the surface must be having a very deeper root below. Okay. And this is what has been shown here, that you have an average of 2.7 or 2.8 is the density of the continental plates, and the density of the mantle is around 3.2 or 3.4, and the oceanic is comparatively high, around 3 to 3.2 or more. But this makes the changes which we see on the surface as well as the deeper part. So overall, this understanding is important because the erosion will keep changing this configuration of the portion which is deep rooted. Okay. So if you look at the this part basically, then what we are able to see is that the horizontally when you keep compressing the material horizontally, then the forces causes shortening. Okay. And at the same time we have that what we see the shortening on the surface, but at the same time the deformed material will keep acquiring and thickening of the crust will take place. Okay. So you have the growth of the crust will be on both the directions. So you have the growth on the surface as well as you have the thickening of that will keep growing within the earth crust. Okay. So you have the roots keep on extending down as well as the elevation which has been picking up here. But this never remains the same because there is an isostatic adjustments, and this cartoons it explains that when you are having the initial stages, you have the mountain building activity, and the crust has been the continental crust is also thickened and having the deeper roots, but this portion, okay, which is exposed to the environment will keep on having the erosion. Okay. So they will be eroded. So erosion and then deposition on either side, but this is reducing the elevation. So as I was talking about that the isostatic balance, okay, adjustment will keep occurring over the time. So this portion will be again raised up because need to be in the equilibrium state. So there is an uplift, and this process can also trigger earthquakes. Okay. And similarly, the time will come when you will have all flat areas and no more thicker part has been left out. Okay. But again, this will keep will be in balance. Okay. So as weight is removed from the top by erosion, the crust rebounds upward. The process of erosion and isostatic uplifting will continue until mountain block reaches normal thickening. Okay. Eroded sediments causes adjacent areas to subside. So what will happen that you are removing the material from here, and then at the same time because you are depositing also. So those areas on the either side will start sinking or subsiding, because this also is because of the loading unloading process. So, any mountains, if you look at, the time will come, okay, but this time is very large, because this will not take place in a couple of years, but millions of years it will take. But usually the landscape will keep changing. So, you are having the young mountain ranges with a deeper roots in the mantle, and the erosion is there, and you have deposition on the either side. This portion will sink or subside, but this will keep uplifting, because it has to balance, the isostatic balance has to be there, and then finally it will die out. Okay. So, those dotted lines are indicating the previous topography which has been shown here. So, this is the first one, the original one, with this line here. So, you have this one here, and this is one here, and this is second one, and this is second one. Okay. And then finally what you see is this one here. Okay. So, this is your third stage, and the landscape what you see on the surface will be somewhat like this. So, finally what we see is the very flat areas where no mountains have been seen, all are completely eroded. So, as we discussed in the beginning, that since the formation of since the birth of the earth, almost like 4.6 billion years ago, we have number of events which have occurred in terms of the tectonic deformation, in terms of on the global scale, and on the regional scale and the local scale. Okay. But for us, as we have talked about, that we are interested in the Quaternary period, and this is the period, and the epochs which have been listed here, Holocene and Pleistocene, are important for us, because this is the time when there was an evolution of the man. And then in this epoch, that is an Holocene epoch, basically we have the onset of the urbanization. So, Quaternary period, mainly we will be talking about that, but if you go on the global scale, then we are talking and getting into the details of the plate tectonics, that is after 225 million years that plate started moving. Okay. So, this part I will start in the next lecture, and I hope you enjoyed, and we will try to cover this one and move ahead into the main topic of paleoseismology. Thank you so much.